Welcome to the webinar, Pre-Concentration Applications for Sensor-Based Sorting and Dense Medium Separation, sponsored by CIM Magazine and Saskatchewan Research Council. I am your organizer, Michelle Beacom, Managing Editor of CIM Magazine, and my co-organizer is Ryan Bergen, Editor-in-Chief of CIM Magazine. Just a little housekeeping before we get started. To ensure you have optimal audio, make sure that you are using the computer audio, if you are using computer audio, that the computer audio button is selected. If you dialed in by phone, ensure that the phone button is selected. If you have any questions during the presentation, please type them into the question box in your GoToWebinar control panel. The questions will be held until the Q&A period after the presentation. And now I'm going to turn it over to Ryan to introduce today's presenter. Thank you.
All right, thanks so much, Michelle, and thank you everyone for joining us today. Today's presenter is Zachary Lang, who is Processing Supervisor Diamond Services at Saskatchewan Research Council. And Zachary, please take it away.
Yeah, okay. Yeah, I'm finishing my master's at the University of Saskatchewan and yeah, registered with Apex in Saskatchewan, and I'm working at the SRC for about 4.5 years. I can share my presentation now. I'll show my screen. Okay. Oh. What is going on? Can you see my, I'm assuming I'm good here. Yeah, so talk about pre-concentration using sensor-based sorting and dense media separation. So just a little bit about where I work at the SRC. We're Canada's second largest research and technology organization, and we've been working in R&D for about 75 years. We're a Treasurer Crown Board of Saskatchewan, which means we are responsible to the provincial government or a minister from the provincial government, and we receive some funding from the provincial government, but the rest of our money comes from contract research and fee-for-service work. So just for to rehash that, 75 years R&D experience and nearly 350 employees. So what is pre-concentration? Well, definitions in mineral processing can really vary quite a bit, and the technology used for certain applications can also vary quite a bit. So we'll make some definitions for the purposes of this presentation and just some generalizations for rules of thumb that you guys can use carrying forward. But for the presentation, we'll define pre-concentration as enhancing the grade, value, and economic potential for before primary recovery and concentration applications. So it's really about removing waste from the stream. That's the primary application. And you see a lot of your benefit like more towards the front. Like as soon as you can do the pre-concentration in the circuit, the better you can do it. The more value you'll get, especially at coarser sizes. So that can really amplify the value when you can do it at the start of a flow sheet, typically on coarser particles. So common methods used include gravity separation, single particle, sensor-based sorting, and bulk sorting, among others. So pretty important concept really in mineral processing, but really for pre-concentration is liberation. And we'll call liberation the degree of homogeny in the composition of minerals within a particle. So liberation can be increased through size reduction, right? So in the white on that particle there, that's gangue. And then we'd call the black our valuable mineral, just hypothetically speaking. So if we break that up, we can have more black material as a percentage of a particle surface when you break it up. So you see we'll have some particles that are all black, and then some particles that are mostly black with a little bit of white. So we've increased the amount of surface area a black particle is covering. And also really importantly, there's particles that are now pure white as well. So dissemination. Dissemination is the size, shape, and composition of minerals within a particle. So on the left here, we have real fine dissemination. So our gangue is still just little black dots. Our valuable mineral is the white. You can see it's really fine particles. On the right, you have coarse dissemination. So really large particles relative to the size of the particle overall. And we can further break that down into fine homogeneous dissemination. So like I talked about before, we have all these really fine particles. They're evenly spread throughout a rock. When we break them up, the particles are still finely disseminated throughout the pieces. So you'd have to break this up quite a bit to really liberate those little pieces of particles. So that's fine homogeneous dissemination. It's equally spread out throughout all the particles. But there's also fine heterogeneous dissemination. So here again, the gangue's in white. and our valuable mineral is actually in the red. And you can see it's concentrated within those black minerals. So when you break it up, you actually are creating a contrast between where the gang's getting sorted to and where the, or you're creating a contrast between which particles have gang and which particles have valuable minerals. Even though it's very highly disseminated, maybe you can't see it, it's still getting there's still a heterogeneous contrast between where the gang is and where the valuable minerals are. So this really all comes together in the idea of distribution. And we can simplify this with an example of a box of, mixed cookies. So distribution is the quantity and location of a given mineral in a sample or deposit of ore. So if we have this variety pack of cookies right here, we may have a bunch of different types in there. We might have a cookie that is 100% chocolate, and working our way down, we have a lightly dipped, or a cookie that's mostly chocolate. It's just dipped, 70% chocolate, 30% cookie, then lightly dipped, 30% chocolate, 70% cookie. Chocolate chips, you have 20% chocolate, 80% cookie. And maybe you just have some with a drizzle, they're only 5% chocolate. And then at the bottom, you have just wafer. You have no chocolate at all in your cookie. And so this is really key to understand, because if this was all individual particles in a sample of ore, this is really how your valuable mineral or the chocolate is distributed throughout your sample. So that's where it's actually located. This is where it's actually available. And where it's actually available dictates how you can actually separate it. And we can sort of make that come alive with our following example. So say we have 6 boxes of cookies with various amounts of chocolate covered cookies in them. So if we looked at number 1, that would be an extremely heterogeneous distribution, right? You only have 1 chocolate cookie relative to all the, non-chocolate cookies. So if we took that over and looked at this graph on the left, you can see that if we separated those by hand, separated those perfectly, well, as soon as you got to 10% yield, you have 100% recovery because you took that 1 chocolate cookie out. But that's not, that can really vary depending on what the grade of your deposit is. So if we go down to 2 and 3, we have slightly more amounts of chocolate cookies. So we have all chocolate cookies and all non-chocolate cookies, really easy to separate. But then maybe our variety pack has half and half chocolate cookies, full chocolate cookies, and just regular ones. So that distribution becomes a little less efficient. And then, so 2 and 3 would be a really ideal case. 4 and 5 would be variable dissemination, but there still is, you can still preferentially sort out the chocolate from the cookie, right? There's still a difference as you go through that curve, because what happens in number 6 is if you have a completely homogeneous distribution. So that's on this graph here. So if you have a complete, like 45-degree line, that's completely homogeneous distribution. That means that the yield is varying directly with the recovery. It's completely spread out throughout the particle evenly. That's no separation at all. So that's, you really can't go past that, but you can have varying degrees of efficiency. So what it seems like is number 1 is the most efficient, and it is because you're removing so much gang relative to what you're recovering, but it's really just dependent on what's possible with the distribution of your. It's not necessarily better. I kind of talk about why. Because different distributions of the same material can really control what your recovery is going to be like. So say we're sorting these cookies, we're taking them out hand by hand, so you're getting perfect separation of these cookies in a hypothetical scenario, but we'll put it back to ore for a second. So say we had low grade, mid grade, and high grade ore. Well, if we started separating that out, again, perfectly, you might end up with, on the low grade, a 30% yield, a 99% recovery, and a 10% grade. That's just, you've perfectly taken it out. If there's only 10% concentration in that material, but you're covering essentially all of it. But you only have a 30% yield because there's only 30% of your material actually has that valuable mineral. So then if we move down to a mid-grade, now you might get a 90 or a 50% yield at a 99% recovery and a 10% grade. So it only the yields increase, but that's because you just have more. If we go back to that other example, you're up from 1 to 2 and 3, right? You just have more chocolate cookies relative to non-chocolate cookies. And same thing with high grade 3, you could get up to a 70% yield on a 99% recovery just because you have high grade sample. There's a lot more minerals or a lot more particles with that valuable mineral in it. And so I can kind of give you some examples of that, because it's really what it comes down to. That's a really important concept. People get hung up on like liberation of the valuable mineral a lot, but when you're doing pre-concentration, it's really about liberating the gang particles. It's about a just having that theoretical difference, that heterogeneous distribution, so that there's actually theoretical separation that can happen independent of the technology, right? So you need to, really the idea is hopefully you can have pure gain particles and just easily identify those from the other particles, right? So even I say it here at the bottom, it's all about having a heterogeneous distribution of the valuable mineral, an identifiable and exploitable contrast between the gangue and the particle containing the valuable mineral. So you need to be able to actually have a difference between what you're trying to separate, and then you need to try to find a contrast. And here's just some examples of that, because it can really vary quite a bit. You could have fine dissemination of gold and quartz, where the quartz can be contrasted with the gangue. So you don't actually need to be able to see the gold. The optical equipment you're using, or to look at it, or whatever your technology, maybe it can't identify those actual particles, but it can identify the quartz. And moving on from that, we have fine heterogeneously disseminated graphite that can be identified by electromagnetic sensors. So maybe optical equipment, it really can't see any of the actual graphite particles, but it can get an overall reading from it just because of the high content of graphite in that particle. And you could also have fine heterogeneously disseminated dense minerals that cause light minerals to sink. You know, so like the gangue could be really light, but you could have enough concentration of really finely disseminated heavy ones that still causes it to sink, still causes it to have an overall higher density. You could also have 1 millimeter lead inclusions at a low atomic density particle. So maybe it's really mostly all gangue, except you have these super concentrated nuggets of really dense material. Well, you could potentially identify it and separate those out. So you just find the particles containing those inclusions. And a similar idea would be a 5 millimeter identifier particle. You have a really coarse grain and a gangue particle. All the gangue could be the same, but as long as you can find those coarse grains, you could eject them out. And then a lot easier example would be just when there's a complete contrast between your gangue material. Maybe you have granite dilution or something like that in your deposit, and it's very distinct from the actual valuable mineral containing ore. So there's just a very clear contrast. You don't even have to have the valuable mineral liberated. You don't really have to have a great contrast between the different types of minerals that are in the main deposit, but if you can identify either a type of gangue or a type of waste or a type of dilution very distinctly, then you can remove it. There's also some wrinkles in there though, and if we look at this graph on the left, one would be a high resolution. This is just kind of an exaggerated example. There's not really a lot of separation going on here, but we call this one high resolution. And as you look wrong, you pretty much get a separation point at each 10% yield interval. So as you're moving through this, you kind of have, there's multiple set points. You could think these are points where you actually have tested and can separate. Okay, so that's resolution you have. And it also, you might be able to extrapolate between the points, maybe you can't. That's really dependent on the technology you have available to you. Maybe like at how fine of resolution you have. Maybe you don't have control to actually pick these points. Maybe you can't actually extrapolate. Maybe these are the only points you can actually operate at. And so if we go to number 2, which is that blue graph above, you can see, okay, it's got good increments all the way up to the last one, where it makes a big jump. And you may be able to extrapolate a point between there, but you might not be able to. Maybe you hit the limit of what, maybe that last point is the limit of what you can actually detect and test, and then the rest of it is just waste. Like you can't detect anything after that. And there's kind of some examples here at the side, like there's a large amount of material between 2 set points. It doesn't always have to be at the end, it could be in the middle. Maybe if you're doing, you know, some kind of density separation, maybe there's a really big concentration of near dense material in one fraction. And so you can't just, you maybe can't devise that interval anymore. Maybe that's the limit of that spread. So that's the limit of the resolution you can separate at. Maybe it's the end of the distribution of material. Maybe there is nothing after the sample. Maybe it's just whatever kind of metric you're using for separation. Maybe there's just nothing after it. And sometimes just the limit of what you can evaluate. So maybe for some reason you can't, the second last point is 3.2 SG on density, and you can't test 3.3 for some reason. Maybe that's it. You can't separate any higher than that. So that's the last incremental point you can test, and then it's just the rest of the material in the sample brings you up to 100% yield. So it's important to understand that, because even if you generate a yield recovery curve from your separation, like we go back to our cookies, you know, even if we get that perfect separation, you mainly only have so much control and where and what you can actually separate. So you might not be able to get to that. Maybe you really want to point somewhere between those lines, but you just can't pick that point and separate at it. So how to approach testing? I'll take you to the graphic on the right here. This is just a stock photo the SRC uses for sensor-based sorting testing idea, but it holds through across a lot of pre-concentration. So you're going to get more information the larger your sample size is, and that can really dictate what you do. But more or less you kind of want to figure out where your minerals are. So if we go back to that golden quartz example, where's the gold? Where is it hosted? You know, what kind of distribution you're actually dealing with. You need to figure that out. And this would also do a lot of liberation studies for other type of technologies in your flow sheet too. But then you move up to pre-feasibility. Okay, so we figured out where our minerals are, maybe have that already. Like you could do some or all of these. It's really up to you. But then you go up to pre-feasibility. Okay, is there a contrast between my material? You know, I know there's a distribution now. Now is there a theoretical? Can I identify the gangue particles and the valuable minerals? Can I have an identification between those? And then once you have that, you can kind of use it as a definition for where you want to separate. And then you can move into an ideal dynamic test. So that's operating an actual dynamic system. So now you have the dynamic principles of the vessel or the technology you're using actually doing the separation, but you run it under ideal circumstances. What is theoretically possible when you're actually operating in this dynamic system? And that'll kind of help you determine where you want to target your yield and recovery and grade and things like that. And once you figure that out, then you would go to a full capacity test. You would fully charge the equipment, see what the actual inefficiencies created by particle and particle interactions, or just running full capacity on a machine or at certain throughputs, what's that going to get you and what's that going to be in your flow sheet. So that's really for when you're developing your flow sheet and your final reporting and figuring out things like that, where you need a lot like more accurate estimation or more accurate estimates of what's going to happen downstream in your flow sheet, especially when if you're removing a lot of stuff and you're sizing your plant accordingly. You just really want to have that accurate. But we can break it down in a few main parts here. So you're sorting minerals, not elements. Like mineralogy matters. You need to know what you're actually trying to separate, and you need to identify your constraints. Is it a brownfield operation or is it a greenfield operation? Could you have a sorter and then speed of separation, or a few types of sorters? Could you have a range of sizes? Like, are you going to be manipulating your flow sheet relative to what the sorter is going to be doing downstream, or do you have a fixed installation where you can only operate in certain size ranges? Then you really are much more limited to what you can put in there. And then, of course, size ranges. These are just rough. They kind of vary depending on the technology, but sorting, you know, you can kind of do for pre-concentration 90 to 6 millimeters, and then dead speed of separation. Typically in these applications, you see a lot of like 12 to 0.6 millimeters, like some kind of size range in there, though there are coarser applications for certain ore types. And then, like I said before, sample size. So, you know, if you only have one piece of drill core, well, you might want to just look at characterizing that and figuring what you have for minerals and how those minerals might react to different technologies, so you can hone in on, you know, if you want to look at XRT or if you want to look at dense media separation. But if you have more material, you can just go and do the test. You can just test XRT, you can just test DMS, you can just test laser. And then representation matters. So going back to our cookie example, you want to have a good representation of what the distribution of minerals in your deposit is actually going to be like, or examples of different types of distribution throughout your deposits, so you can sort of normalize and predict for that. Because, you know, if you test on having 3 chocolate cookies and you know, 7 non-chocolate cookies, if that's your kind of ratio, and you separate that perfectly, well, you could undersize your plant. But if you do it the other way and maybe you're overestimating, maybe you really have a deposit that has 5 chocolate cookies, 5 non-cookies, and you get a sample that has 7 chocolate cookies. Well, now when you go to make your plant, it may be way oversized for what you need. That kind of thing. Like you may not be getting the amount of, you may get too much material, not enough material, depending on what you actually expect to remove. And then the testing phases, which I kind of went over already, but again, like you have a static test to see where the contrast is, an ideal dynamic test, how can this really separate under ideal circumstances, and then a capacity test with how much throughput can you actually get and what are the compromises you're going to get in your efficiency. So we'll get into single particle sensor-based sorting first. We'll kind of work through some examples of that. With single particle sensor-based sorting, there's really 5 main steps in it. The first one is material conditioning. So that's sizing your material appropriately. So that's where that where's the liberation of your gang kind of in, right? Like you need to make sure it's the right size. So that'll be crushing and screening and that kind of stuff. Things need to be liberated. They also need to be clean. So you might need to, depending on the technology, like XRT, for example, something like that, it can see through like a thin layer of mud or something on the top. But something like laser, you know, where you're trying to penetrate through a transparent technology, you need to have that clean. So there's cleaning. There's also moisture, depending if you're using a belt or a chute or if it's water fed or whatever. You could have caking in the machine, which can cause just actual mechanical issues. So you really got to prepare the material so it's the right size and also the right size ratio. Typically in sorters, you can kind of push this a little bit, but you typically operate in a 3-to-1 size ratio, and that's just so you don't get inefficiencies. You're less likely to get inefficiencies in the machine. So you kind of want that 3-to-1 size ratio just as a rule of thumb. So you need to make sure it's sized and ready for the actual sorter. And then step 2 would be the material prep or presentation. So you've already fed the material to the sorter. Now you need to make sure that it's getting presented to your detection technology properly. So in the example we have here, it's like a belt fed sorter, and you can also have chute fed. But in this scenario, you kind of have like a little chute or a little pan feeder that would drop it onto the belt, and then the belt would spread it out in a single monolayer. That's what you're trying to do, a single monolayer where the particles aren't touching, but the belt is as full as it can be. And the reason you want to do that is because if particles are too close or they're overlapping, you could have particle masking. That's also another reason for the 3-to-1 size ratio. It's a lot easier for large particles to cover small particles if there's a big range in sizes. But you want to prevent masking. You also can, some sorters will have issues if you have particles touching. They'll identify them together. It'll confuse the sensor. So that's what you're trying to do. You're trying to present it to the sensor in the best way possible so it can see the particles individually and as accurate as possible, because that's really the crux here. You're sorting individual particles. That's how you really get the high resolution and the high separation. So we move on to the sensor itself. And so that can take a few forms, and I'll discuss them a little bit later, but the idea is essentially read some kind of signal from your particles and then can identify them individually, regardless of what that technology is. So, and then step 4 is the actual data processing. So I'm going to see, the sensor will actually see the particle, and then the data processing will take that signal and convert it into a quantifiable metric. So you get a signal, you turn it into a quantifiable metric, and then you can start and make decisions. You can program the machine to make decisions. Say, okay, if it's chocolate cookie, I'm going to eject it. If it's 50% chocolate, I'm going to eject it. Things like that. So it takes a signal, turns it into a quantifiable metric, and then makes a decision on it. And then it also has to then figure out where that particle is on the belt, because we have a side view of it, but the belt would actually be like all the way across. So in this example, we would have a belt. It's a belt with air ejectors. So there's going to be air ejectors scheduled kind of like in intervals along that belt, with the idea being that so then when particles are moving along the belt, you can pick individual locations as it goes over the ejector to actually eject stuff. And that's how you get those individual particles to separate. So this can be a real limiting factor with the technology because it's very computationally intensive. In this example, you may have a belt moving 2.7 meters per second. And depending on the size of the particles, you could have hundreds of particles or thousands of particles on the belt. So in a few fractions of seconds, got to see it, identify it, make a decision, and then eject it in a certain spot. And that's what happens at that step. And kind of what I've alluded to, step 5 would be the separation. So in this example, if you fall 5 over, you would have like an air ejector, but you could also add mechanical flash, like flaps or any other kind of mechanical action to remove something. But that's really the part where it goes, okay, I see a particle here, I'm going to line it up, bang, I'm going to take that particle up, but I'm not going to take the other ones. And that's where the resolution really comes in. And that separation turns stuff into either a non-ejected fraction or ejected fraction. The terminology can change a little bit depending on what type of flaps or separation you're using, but that's more or less what happens. You put one in one stream and one in the other stream. It could be accepts and rejects, but we'll just call it ejected fraction and non-ejected fraction for now. So really, you can kind of break the machine down into 2 overall areas, and that's what's happening with the sensor, and then all the other mechanical actions that are happening, whether it's presentation or the actual separation mechanism. And this is important to understand because this is where the different types of inefficiencies can come in. So I talked about making a contrast. So what you want to do in this is make a definition for what the sensor is going to see. And if you have it properly calibrated, everything should be good. But if for some reason you don't have a proper calibration, or there's some kind of not properly sized material, let's say, introduced to the system, you could misidentify a valuable particle as a non-valuable particle, in which case, let's say we're ejecting valuable particles, it wouldn't get ejected. And then you get the flip side too. If your definitions aren't good, you could identify waste as a valuable particle. And now you're just adding yield to your product stream, and you don't want to do that. But that doesn't happen too much if you set up the sort of properly. What's more of a concern are the mechanical inefficiencies. So there's really two types of them. There's incidental ejection. So that's if, like, for this example, if two particles were moving over this belt and they're very close to each other and the ejection mechanism fires, well, it'll eject the particle you identified for ejection, but it might also incidentally clip another particle, and then they both get ejected into the bin. So if you were ejecting waste, you might get the waste particle and a piece of ore might accidentally go. And these don't happen at high frequencies and high volumes, but there is a difference between that and actually what's happening ideally. And then the flip side of that would be, you know, if you're trying to actually eject a particle and you get sort of a glancing blow on it, you don't hit it straight up because whatever issue with mechanical setup of the machine, you might accidentally eject that particle, or not eject that particle into the bin because it doesn't get enough force to actually move it. And so those are really kind of the inefficiencies you got to be aware of when you're dealing with the machine. So there's the sensing, is it actually seeing it, and then the actual mechanical action. So types of sensors. There's quite a few, and there's going to be more developed. It's really, when you're using a sensor, it's all about finding something that can contrast the gang most effectively for you. And these are just some common options available. So XRT uses X-ray attenuation. It can be used in base metals, precious metals, coal, diamonds is pretty popular. You have XRF for elemental composition. XRL is X-ray luminescence. It's really popular in diamonds and it has been for 50 years. It uses a visible luminescence response created by exciting the particles with X-rays. You got laser, which I kind of talked about earlier. If you have a transparent particle, the X-ray will penetrate. If you have a not transparent particle, it will absorb it, and you can read the signals like that. And then there's really the most basic and easiest technology, if you can use it, color. So it's really just looking for a visible difference. Is there a visible difference between my material? And we've all dealt with this before in your life. You're really just looking for a contrast. So at the bottom here, these are my fancy bottles, but say if you were recycling something and they're sorting it by color. Well, you might have a green wine bottle and a brown whiskey bottle. So, you know, you put the green bottle in one bin, brown bottle in the other bin. And that's really what this contrast looks like, is you're just looking for a difference. But, you know, glass from metal or plastic from paper, or a green bottle from a brown bottle. All right, so how does this test work actually look? We talked about these types of tests before. Now let's see what they look like actually in a sorting application. So for a static contrast test, typically you're going to use like a test sheet. It can vary a little bit depending on the technology, but the idea is that in a controlled setting where you're not actually exposed to the dynamics of the machine, you're going to test the sensor. And what you'll see is there a contrast between gang particles and product particles? And this can be a few things, like you could have high grade, mid grade, low grade, barren, or you could have specific types, specific minerals, like specific types of gang, specific types of product, or just ore that contains product and ore that contains gang. And you'd set that up to make your definitions and see if there's a contrast between the things you want to keep and the things you want to get rid of. And so assuming that all goes good, you do your test and there is a contrast. Well, you can use that as the definition and then set up the sorter for the next test or the next stage. So you find that contrast, and then what you'll do is you use that contrast in the sorter. But it might vary a little bit because you could probably control the percentage of that signal you want to see. So if it was if we were able to find a sorter that could identify chocolate relative to cookie, and we know there's a contrast there, then in the next step we decide, okay, well, how much chocolate do we need on a cookie to want to separate it? And that would be kind of the idea. Is like we might start off with, well, I only want cookies with 80% or more, and this is where you get like a yield. You'd want to generate a yield recovery curve, so you kind of figure out where you want to operate in your operation, like where's the cutoff. So you might start on the top. You do a cascade, and so you go, okay, I'm going to separate the 80% chocolate cookies, then move down to the 60%, then 40%, then 20%, and then all the way down to 5%, and then maybe you're using XRT and you want to look for inclusions, and so you have chocolate sprinkles on the cookies, and then you want to, okay, well, if it has 1% of the area is a sprinkle, I'm going to eject it, right? That's what I'm going to take away, and you use that to generate your yield recovery curve, so you can kind of figure out how you'd actually operate. What set point, back to that resolution, what set point would I want to operate on? And then we could go to the high capacity sorter test. And so that's after I've picked out the set point I want to go in. And usually if you're dealing with waste removal, the idea is you want to keep all your valuable product and just remove waste. That's usually what it is. So you always try to push it to kind of like the nth degree of what you can detect for your valuable mineral relative to the gang. But once you figure out that point, then you can go to a full capacity test. So this is where you run the machine fully charged. You're going to have those particle and particle interactions. You're going to have those mechanical inefficiencies. And then you can see, based on theoretically what can I achieve, what can this machine actually do. And the ideal test is really important relative to this because the technology is moving really fast and there's lots of different types of sorters, and they can all have different pros and cons for your application. And also, sorter manufacturer can customize a sorter for your specific, like the specific characteristics of your rock. So when they do that, they can compare it back to this ideal, and you can see actually what the separation is, right? But also you can do a full capacity test on a sorter just to see, you know, if I was using this or using natural sorter, what's a close approximation of what the performance would actually be like, or at least a performance indication, which you know you can get. I didn't talk about this too much at the start, but pre-concentration, it's really important to understand, you know, what's going on with your ore, so you can tailor the application, whether it's gravity separation or density separation or sorting or whatever. So you can really tailor it to what you have going on and get the most efficient and effective separation. Oh, jump to slide there. So let's talk about X-ray transmission a little bit specifically. We'll do some examples in this just for a specific type of sorting technology. So X-ray transmission uses X-ray attenuation to measure particles, but this is really a function of atomic density, so the amount of atoms present in a given area, and then the thickness of the particles, so the height of the particle you think of, and then the actual density of the particle, so the weight over the actual volume. So if we can kind of visualize this as jars full of marbles. So what the X-ray attenuation really is doing is it's counting the number of atoms, but you can also think of it, it's counting the number of marbles in a jar. So if we have a small jar of marbles with large marbles, our X-ray attenuation would be the number of marbles in that jar. But then say if we had the same size of jar with smaller marbles in it, well, now we're going to count that number of marbles. So that would be the that would be the X-ray attenuation, right? So we all of a sudden have more marbles in it. But then also if we had a taller jar, well, we can also get more marbles in that. So you can see based on the X-ray attenuation how, if these were actual particles and you're counting up the marbles, how that could really vary based on thickness and that atomic density, because the atomic density could really be the like the size of the marbles, and then the thickness could be the height of the jar. So it's not a good approximation for atomic density is atomic number. It's not an exact measure, especially when you get to complex mineral compounds, but a good example would be diamonds. So diamonds will lots of times be concentrated using dense media separation. So diamonds are very dense, 3.53 specific gravity relative to the gangue, which is typically a 2.7 specific gravity for kimberlite. So use dense media separation, diamonds come out with other heavy minerals. And so then you can use XRT to cause a further separation. But actually what happens in there is those heavy minerals are typically iron-bearing particles or magnesium-bearing particles. They're pretty atomically dense relative to carbon, which is not. So when you do an atomic or X-ray transmission separation, you're actually looking to separate out the low dense atomic particles, which are the carbon, relative to the high dense atomic particles, which are often iron bearing. So what's dual energy XRT? Because this is the actual technology you'll typically run into. This is an X-ray transmission unit that has one X-ray source and two sensors, and it essentially just uses a high energy and low energy reading to normalize for thickness. So it can distinguish atomic density regardless of particle thickness, at least to a point. They see things kind of break down a little bit in the physics after a 3:1 size ratio. Density, of course, is also a factor, but as you can see from the diamond example, it's a lot smaller one. So how this actually works is if we go back to our jar of marbles where we had the short jar and the tall jar, when you use X-ray dual energy X-ray transmission, you normalize the size of that jar. So it's always going to see, like, count the number of marbles from the same size jar relatively. So it normalizes the height of your jar. So you're always reading, like, the size of your vessel is always the same. So then it's really more about the size of the marbles in your jar. So what does this look like in actual application? Well, when you take your readings from the sorter, what happens is you'll classify particles. So you can pick a point in it on a graph essentially, and this black line right here would be the point of separation. So if you get a particle based on your two energy readings that gets classified underneath the line, well, it's going to be low. It's going to be low atomic density, and if you get something above the line, it's going to be high atomic density. You can manifest that in a test sheet. So if this was rocks taped to a test sheet, you can kind of see that the rocks or parts of the rocks are going to show up high dense and low dense and get classified right on there. And this is important. So you're going to set a definition based on your contrast, and then you'll go, okay, this is going to be high dense and this is going to be low dense, which ultimately manifests in yes and a no. So what you'll do is you'll set your high dense thresholds, and then you maybe pick a percentage of, we'll go over a little bit more, a percentage of particles that you want to be. So maybe we want, if we're classifying chocolate as blue, maybe we only want 90% blue particles, or maybe we're okay with 5% blue particles, but you set a definition and then it's a binary yes and no. And that's where sorting really kind of differs from a lot of processing technology. You're not going to pull more yield necessarily linearly as you pull more recovery. So you can't just pull harder to get higher yield, get higher recovery. It doesn't necessarily work like that. There's a non-linear relationship there. It's always a decision on yes or no. So each time it's seeing a particle or the hundreds of particles on the belt, it's making a yes and no decision for each one. So if we go back to that perfect separation table where we had that low grade having a 30% yield and high grade having a 70% yield, this is where you can really see it, because it's going to separate the type of particle the same way every time. So then it comes down to what the distribution of those particles is like for your actual separation. So let's go through some examples of that test work stages. So a static contrast test. Here's a spodumene pegmatite. We have it at the top, and then so there's spodumene, and then quartz, and then feldspar, and then mica. So spodumene is what we want. Don't want all the other stuff. However, when you actually do the test, we'll run it through the sorter. This will be the raw XRT image you generate. So we got spodumene at the top, and then quartz, feldspar, mica, like we showed before. And it's typically 10 to 100 rocks, which you put on a test sheet, depending on what you're trying to do. So we'll run it through the X-ray, and like I talked about, we'll generate that definition, or we'll generate those contrasts. So what we're seeing here is we have low density, so that spodumene and that quartz is coming out as low density, and then we have the feldspar and the mica as high density. So there's pretty solid contrast between the low atomic density particles and the high atomic density particles. You could probably separate those pretty effectively. So we can break that down and look at it a little closer. So again, for spodumene, which is our lithium-bearing compound, we have our X-ray image at the top, and then you actually have the image identifying with the what the particle is. So that's the machine going, okay, there's a particle there. This is what the particle is, and that'll really come into play when it's trying to get separated. But then on that particle, it'll overlay your signal, your contrast signal. So how much that particle is red, how much of that particle is blue, and that's based on the atomic density. And then at the bottom, you can just see the image. So this is the particle we want. So then we have the feldspar, which we don't want, which is our potassium-bearing mineral. And we again have our X-ray contrast at the top, and then we have the actual image identification, and then we have the actual classification as high density or low density, and then at the bottom we have an image of it. So we have a pretty good contrast between the high dense feldspar and the low dense spodumene there. And it just happens to line up with our table again, right? Lithium has a lower atomic number, and also in this case a lower atomic mass, actually lower atomic density, and then the potassium has a higher atomic density and a higher atomic number. So here's another example too. So there's not just dual energy XRT, there's single energy XRT, and you can use those together. So I was talking about inclusions earlier, and this is where it comes into play. So this would be like a lead zinc particle, and you can even see in the X-ray image there that there's like tiny black particles there that you can almost kind of see just even from the X-ray. So if we go over back to our image, where you're just classifying the image, we could also overlay that with, are we seeing hyper dense particles? And these are those inclusions, those really small inclusions. And this is a really heavily included piece of rock, but you can have rocks where you can identify individual inclusions of them. Maybe there's only one, but you still want to get that inclusion because that's where all your grade is concentrated. You can identify that and you can separate that. But you can also use, we talked about that atomic density separation and then these really high density inclusions. You can use them in combination. So on this particle over here, the red is low density, the blue is high density, the black is inclusion, and then the purple is where black and blue overlap, so where inclusions and high density overlap. And you can use that in combination because maybe you have particles, you're trying to get a few different things out of your ore, or maybe it's spread on a few different types of minerals. So you want to make sure you get the high dense minerals and you also get the inclusions, and that can give you a lot more control over your separation. Alrighty, moving on. So that's what we did our test sheet. We created our contrast test. Now we're going to do that ideal dynamic test. We're actually going to test those percentage of inclusions and high density or of high density. This is where we test that. So you can do tens of kilograms to hundreds of kilograms. You can do 10 kilogram bucket, 20 kilogram bucket, 100 kilos. Depends on what you want to do for your project and how representative you want it to be. So we would adjust those thresholds, like I said, percent of classified attenuation in the particle. So we'll show you, I'll make a yield recovery curve out of that. And so this would establish an ideal threshold in the yield recovery curve, right? Under ideal conditions, that's the really important part. And these are cascading separations. So again, you're going to take off the chocolate cookies of 80% and the chocolate cookies of 60%. So that's how you make that curve. And these splits are typically submitted for assays on site. So in this photo, I guess I'll go back over here. This is the X-ray transmission sorter we use for our test work. We only have one X-ray transmission sorter that we use for it. Despite what this diagram shows you, we only have one, at least of that type. And so we run them through in passes. So the first pass would be you run it through and you get an ejected fraction. That 80% chocolate comes out, that'd be fraction 1. So the stuff that didn't get ejected would go back through another pass through the sorter at a lower setting. So at 60% chocolate, so that'd get fraction 2. And then we do it again, it gets fraction 3. And then if you're only doing one more pass in the cascade, then you'd run it through the sorter and you would get fraction 4 would be what's ejected, and then finally fraction 5 would be the final material that was not ejected. But say we did 6 separations just for an example, and this is something you can definitely achieve depending on the type of ore in your plant. We've seen things like this before. So you get a 55% mass yield threshold and achieve nearly 100% of recovery of the mineralized ore. So that means a pretty good contrast between where your ore is, and you can identify it, and where the gangue is. So we're removing roughly 45% of the non-mineralized ore, the non-valuable mineral bearing ore. But what this kind of turns out to is that first cascade would be separation 1. The second cascade, or that second ejected, would be separation 2, and then 3, 4, 5, and 6. And 6 would be, the final tail separation. And so you can kind of see what your resolution would be like. You might not be able to extrapolate between 5 and 6. You might be able to, depending on the thresholds and the technology you're using, but those would be the actual test points you're using to try to generate that yield recovery curve. And so that would be the ideal dynamic test. And then you would take the set point, let's say that 55% of the mass with a nearly 100% recovery seems pretty good to me. And then you'd move on to that capacity performance test. So it's a larger volume. It can be hundreds of kilos to tens of thousands of kilograms. And it's really for optimizing your flow sheet design. And it's going to see that ideal performance versus the actual realized performance in the mechanical inefficiencies. So what kind of throughput can I put through, and what kind of trade-off to my efficiency am I going to get? How many misplaced particles am I going to get, and what does that actually mean for my yields and my recoveries? So this is a pretty exaggerated example, but there's kind of 2 misplacement, like I talked about, that can happen. You can have waste misplaced into your value stream, or you can have valuable particles misplaced into your waste stream. So just for this example, we'll go through one which is more typical, because usually if you're worried about your valuable mineral, you'll eject, because you can it's more common to fail to your ejects, so you probably eject your waste. But we'll say we're misplacing waste when we're trying to eject your valuable materials. So what happens? Well, if you look at the ideal graph or the ideal curve and the realized curve, what's happening is you're getting the same recovery, you're just getting a lot higher yield, and that's really affecting the efficiency you can get out of the sorter. Again, it's pretty exaggerated, but you can see here at the start you almost have a 10% offset in the yield at the same recovery just because of misplacement, theoretically speaking. So moving on from there, we're kind of running out of time a little bit, so we'll move on to gravity separation real quick. Gravity separation is really just separating low dense material from high dense material. So this is how we would do our heavy liquid separation test. You have a liquid of a known specific gravity. The stuff of a higher specific gravity will sink. The stuff of a lower specific gravity will float. And if any of you have gone panning for gold, it's the same idea. Gold's pretty fine grained, but you're able to preferentially separate that from the rest of the particles. And if we wanted to bring it back to a lithium example, is there a theoretical difference? Well, we could look at the specific gravity of our minerals, and albite and quartz, 2.6, 2.62, we don't really want those. Muscovite, maybe take it or leave it. And then spodumene is what we really want. So there's a pretty good contrast there theoretically. And then DMS cyclone, we can kind of break these down into stages similar to when we were doing sorting. So ore comes in, stage 1, crushing and screening. This is that conditioning. Make sure you have the right particle size, taking consideration liberation of your gangue and liberation of your valuable mineral, and then the percentage of near density material, because that's going to make an impact on your separation. And then we'll take the ore and we'll take our circulating media. So what that really is you can make a Newtonian fluid by suspending fine particles in water and keeping them suspended. So it acts like a fluid of a specific density. So you can combine like fine, heavily dense powder with water in specific ratios to control your density. So you'll combine that in a mixed box, and that's that presentation, because you want to have a proper ore to media ratio to make sure that the ore is interacting properly with that circulating media. And then you combine them and you put them through the sorter. So this is a dynamic system. You have essentially a big cyclone happening in the inside, which will cause the material, when it's using a media and kind of on its side, to separate based on density, not on gravity. So a hydrocyclone, you'll get liquid and size differences, and there's a little bit of size bias, or there are size bias considerations in a dense media cyclone as well, but it's mostly separating based on density. And so number 3, our separation, it's based on the pressure, the media density, the particle-on-particle interactions, your spigot size, but stuff will come in, it's pressurized, and then floats will come out the top, like the light density material, and then the high density material will come out the bottom in the sinks. So what are those stages? And we'll relate those back to sorting. So what's our static contrast test? Well, that's that heavy liquid separation. So we're going to get a profile of the minerals in our sample. You're going to get a profile of the density, because the density spread of the material, and you can also do that by size. So it's kind of similar to particle size distribution, except it's across density, but you can also do it times by different particle sizes, just to kind of see where the minerals are in different sizes. So when you do that, you can kind of get an idea of, okay, is there a theoretical contrast here, and where would I want to potentially operate? And that's where you go up to the next stage, which is the DMS cyclone test under ideal conditions. So this would be really high dilution of your media, limiting those particle-on-particle interactions, limiting maybe potential inefficiencies in the cyclone design. And it would give you that actual dynamic separation, which we'll talk about a little bit more. And then finally, you'd have the capacity dynamic test. So that's where you're going to fully charge a cyclone. You're going to get those inefficiencies. What are we actually going to realize if we were in operation? I'll break that down right here, because this would be the results from a heavy liquid separation test, kind of simplified, but the idea is that each density increment, you would get the amount of material, like so the amount of the mass, and then the actual percentage of your valuable minerals. So some, just for your reference, in spodumene separation, lots of times you'll get like a reject in your very light fraction, and then you'll have the stuff in the middle that's a pre-concentrate. It's not high enough. You might need to upgrade again with flotation. But then also on the other end, you can get a very high, like a concentrate, really high amount of your valuable mineral that you maybe can skip flotation. But for simplicity, we'll say that we just want to do one separation. So we're kind of looking to separate around 2.65. Like, we'd really like to keep everything 2.65 and above. That'd be pretty good separation for us. Unfortunately, in a dynamic system, it doesn't work like that. So what you have in a cyclone is you have a D50, or that point at which there's a 50% probability that particles could go to the sinks or to the floats. And there's also a gradation, as you can see in the left-hand side figure, between where you get to 100% of the material going to the sinks and 100% of the material going to the float. So there's a gradation. And over that gradation is where you get inefficiency. So, you can get ore misplaced to the waste, and you can get waste misplaced to your product stream, right? So you kind of have two things going on there. And so we'll break down 2 examples here. So say we had a Cartier probability moyen, that's EPM of 0.05. So that's the kind of shape, or that's how steep that curve is. If it was 1, it would be completely parallel. That'd be perfect separation. And horizontal would be no separation at all. But we have right there 0.05 is pretty good. So in this hypothetical example, say we're getting 90% recovery and a 35% yield. Well, if we aren't getting as good a performance in the cyclone, say we go to the right, well, we have only an EPM of 0.1. Well, if we want a 90% recovery, we're going to have to lower our set point. So instead of having that D50 at 2.75, we might have to have it at 2.65 to get a 90% recovery, but then our yield's up to 55%. And you could really also think of this like, if you had say on the one on the left, if we were doing an ideal separation with, you got 0.05, that's great. But maybe when you actually did it realistically, you got 0.08, something like that. So it's a little bit of a lazier curve. So now you're getting more displacement, worse performance. You might have to adjust your set point to really meet the minimum thresholds for grade or recovery. And that's that. Ideal gives you how good it can be, and then the capacity test, so how good is it actually going to be. So here's the key points. Let's wrap this up. Heterogeneous distribution is the key criteria for pre-concentration. Then you need to find contrast. So is there an actual distribution that you can exploit, and then can you actually find a contrast to exploit it? And the 3 stages: static contrast test, ideal dynamic test, and capacity test when you're actually trying to evaluate it. So pre-concentration at the SRC, just real quick, we're independent. We work with mining companies, equipment suppliers, and contractors. We have assays and mineral identification services on site. We have crushing, sizing, heavy liquid separation, dense media separation, and bench and pod scale sorting test work. Our headquarters is in Saskatoon. We have offices in Regina and Uranium City. And here is my email and phone number. Feel free to reach out if you have any questions.
All right. Thank you very much, Zachary, for that presentation. So if anyone has questions, just go ahead and you can enter them in the question box in your GoToWebinar control panel. And we do have some already. And they are rich in acronyms. So I'm going to do my best to get these right. So someone would like to know if you could maybe just touch on a bit on size frequency distribution that you can get from XRT, and how reliable is the data?
Oh, okay. So yeah, so that's probably a long question, so I'll just give a short answer for now. Yeah, you could get some size information off of it theoretically, depending on which technology and which vendor you're using. But yeah, so when you're scanning, I had that diagram of those green particles, so you can see the particles, and you can see the length and width, and even get an idea of the thickness. So you can kind of get an idea of the overall mass of a particle going through your machine, and they can actually be fairly accurate. Now, depending on if you're doing actual laboratory testing or running in a mine operation, will really kind of vary the quality of that data. But yeah, it can theoretically, well, not theoretically, it can measure it, and it can be pretty accurate. But I can answer that more in depth because there's some kind of wrinkles there at a later time.
Well, yeah, and of course, yeah, your contact information is there. If anyone wants to follow up and doesn't get full satisfaction on their question, yes, I would definitely encourage you to.
I guess I should say back that point, XRT can do it. Other technologies can do it. It's just got to have the right sensor in there to actually identify the particle rather than just the signal. Okay, we can go to the next one.
Okay. So how can you monitor online the performance of a SBS in a production environment?
In a production environment, well, again, so I was talking about laboratory testing here. When you're actually asking about specifically how you're going to do that, that would have to be working with the vendor, the people actually selling the sorter. So they would have to have some kind of system set up to be able to monitor the signals and then essentially cache them and then organize them for your using. So you'd really just need to talk to the vendor. There are options out there for that where they can give you statistics off your machine, where on the belt you're getting most material, what kind of material you're getting. And I definitely think it's a good question because there's definitely the potential there when you have these, sorting units where you're identifying things, you're sensing particles that are going through, to implement that into process control designs at some point, especially with some of those AI models, because you could get real-time data off it. But the best answer would be talk to a vendor, and you can reach out to me after, and I can provide some more in-depth information with that. But reach out to a vendor and ask them what they have for services for real-time product monitoring or real-time monitoring from the machine.
Okay, great. So somebody asked about the relative costs, I guess, both in CapEx and OpEx of dense media separation versus XRT. Okay,
yeah, good question. Well, there's a few considerations in there. Sensor-based sorters can be very expensive and can be limited by your size ratio. So they become a lot more cost effective when you can use them in coarse sizes. So 10 to 30, 30 to 90, you can get a lot more capacity. So just for example, like the belt example I showed you, it gets the capacity, if you can only fill the belt so much, gets limited by the actual thickness of the particles. So the coarser your particles, the more you can get through it. But they can be hundreds of thousands of dollars. So they can be quite expensive, but they can also be like very, very effective, very, very high throughput. So it really comes down to, are you going all the way down to 6 millimeters? Like what sizes do you need? How many sorters do you need? So the individual sorter can be quite expensive if you need quite a few. As for like the DMS or density separation, like cyclones themselves are a lot cheaper, and you need but you also need all the infrastructure and the pumps to go along with it. So DMS, probably a little bit cheaper if you already have the infrastructure, but if you have to put the infrastructure in place, it kind of depends. Like how many sorters do you need? How many cyclones do you need? Because you can get a lot more bang for your buck out. Like it's easier to get multiple cyclones in one installation than it is to get multiple sorters. That helps.
Thanks. So what is the throughput capacity of the XRT sorter at SRC?
What's the capacity? I believe we can go up to, like, again, it's kind of commodity specific. So like I talked about, like if you have the belt fully capacity and you're dealing with the thickness, well then density also comes into play. So the denser your particles, the higher your throughput is. If all the like if you had round marbles on a belt, then density would really be a factor that controlled the capacity. But up to 60 tons per hour probably would be there. Maybe some slight differences depending on the commodity and the size range. But if you're like coarse particles with a good density, you could get up to 60 tons per hour, maybe a bit more.
Okay. And when it comes to sulfide minerals, is there one that does DMS or XRT generally perform better than the other?
Oh, that's I'll say from a general point, that'd be one I'd be easier to like answer offline, but it really depends on the mineralogy of them. Like if you can identify the sulfides accurately with a given sensor technology, well then you can separate them super easily, but it also depends on like the size of your ore. And so then if you get down to using DMS and they have a greater effect on your particle, like how coarse are they, right? So if they're coarse enough that they can have a distinct separation from the gangue in DMS, then that's good. Or if there's enough of them present, like I talked about in a particle depth separation, that's good. It really just depends on the specifics of the sulfides you're treating and the background mineralogy. Like that's a more specific question. I don't mind kind of talking offline just because we only have a little bit of time left.
Right. Yeah, indeed, we do only have a little bit of time left. So maybe just one more question, and then we'll wrap it up. Yeah, again, we won't be able to get to them all, but you can find Zachary and at that number and that email address. So, question is, in an operating mine, what would be the ideal top size of the ore particles for XRT ore sorting? And top size, I assume, means the maximum size. This is related to the heterogeneity. Okay,
well, it's all about distribution. So, like, ideally, as coarse as possible. Like, that's really where, like, the coarse you can get, the more it's possible. XRT, for the most part, is limited at kind of that 90 millimeter top size. So if you could do 90 to 30 millimeters, that 3-to-1 ratio over there, that would be ideal. Because the coarser it is, the more capacity you can get through it, the less like units you need. Yeah, like the lower capacity, less units you need, the more effective your separation is. But it's really about if that gangue is liberated at that size. So if you have dilution and it's really clear and you can do it at 90 millimeters, that's great. Otherwise, you know, sometimes it's 60 millimeter top size, sometimes it's 50, sometimes it's 30, 10 millimeter particles. But yeah, as coarse as you can go would be the simple answer for that. But that's really limited on the distribution of the minerals in your deposit and how well that gangue gets liberated.
Awesome. Great. Thanks, Zachary. So that pretty much does us in for time today. Thanks again, Zachary, for your presentation. If you have any questions, you can reach out to him. Yeah, we'll be, thank you again. Michelle.
Thank you, Ryan. And thank you, Zachary, for that interesting presentation. I'd like to thank all our attendees and also to let you know that any questions that didn't get answered that you've typed into the question box will go to Zachary after the presentation. And also after the presentation, I'd like to ask you to please fill out the short survey that pops up on your screen at the close of the webinar. A link to the video recording of this webinar will be emailed out to you tomorrow. We hope you enjoyed our webinar. For more online presentations like this one, please visit the CIM calendar of events on cim.org. We hope to see you at our next webinar. Thank you.